Yeah, okay. So in yesterday's class, we were discussing something about multiplier, right? So what are the things that you have learned inside the multiplier in the chat, guys? So while discussing about multipliers, we also know that inside multipliers, we are also using another operation is called as arithmetic operation is called as like adders, right? So however, in real world processors, DSP systems, GPUs, AI accelerators, and communication system, multiplication is performed much more frequently than we realize, right? So, yesterday class, I said right in which domain we are going to use these multipliers the most. Guys, answer the chat. So, what is the real world scenario where we are going to use these multipliers the most? No answers. Oh, okay. So I said something about AI accelerator, right? So did you guys find about something about AI accelerators? So okay, no answer. So I consider no one has discussed. Okay. So if I give you guys some task, okay, so just complete it on that particular day. Yeah, like it doesn't take that much time to research on that. What are the AI accelerators? Why use multiplier? We use multiplier inside that, right? So just go and home search search in your free time search what is the thing my AI accelerator is called as and why we use multipliers in that. Okay. So coming back to the topic. While learning multipliers, the challenge is that multiplication is much more complex than addition, right? We also discussed about this topic, right? Why? Because inside multiplexer we use a number of addition adders, right, for addition purpose. So that's why multiplexers are complex and use a larger area, silicon area, right? So just think for a n-bit multiplication, we need to generate many partial products and then add together, right? So that's why while discussing about multipliers, we just there are two steps. One is called as partial products, and another one is called as a partial products addition, right? Sorry, generation and addition. Okay, these are the two stages that are going to occur inside the multipliers. Whereas in these two stages, to add that partial products, we require many number of full adders. So that's why because of these, like VLSI designers developed different multiple multiplier architectures. Okay, so what is the purpose of designing these multiplier architectures? To to minimize the use of adders inside the partial product addition. Okay, so that's why VLSI design developed some of the architectures. So in that some of the architectures we have something called as array multiplier, booth multiplier, and Wallace tree multipliers. Okay, so these are the three multipliers that we are going to learn in today's session. Okay, so just enter into the topic. We should do a small comparison between these. Okay, so array multipliers are the simplest architecture. Okay, booth multipliers reduce the number of partial products. Okay, just keep this one word. Okay, what is the main thing that to remember inside array multiplier? They are the simplest architecture. In booth multiplier, they reduce the number of partial products, whereas in Wallace tree multiplier focuses on maximum speed. Okay, so today we will understand all these three in detail. Okay, including their architecture, working advantages, disadvantages, and industry applications. So array multiplier. So the array multiplier is the simplest hardware. Okay, well, just like I said, right? Array multipliers are the simplest architecture. So like that only, the array multiplier is the simplest hardware implementation of binary multiplication. Like how we learned something about like how the multipliers works and how the multiplication is done inside that multiplier. We discussed these kind of things, right? So array multiplier is the simplest hardware implementation of binary multiplication. Okay, so it's just like the mimic of that binary multiplication. So what does this do? It follows exactly the same method that we use when multiplying numbers manually on the paper. Okay, like when we were child, like when we were children, we have done like multiplication, solving multiplication on the paper, right? Like how we used to do on the paper, right? Do you guys remember that? So in the way that we calculate or multiply numbers manually in the paper, based on that same method, array multipliers are designed. Okay, so just like I said, a multiplier in multiplier multiplication process consists of two stages. What are that? Partial product generation, partial product addition. Okay, in first stage, each bit of the multiplier is multiplied with, like each bit of the multiplier is multiplied with every bit of multiplicand using AND gates. Correct, right? So that's what we did and learn in the previous classes. Okay, just remember, if you are multiplying anything with 0 or 0 with anything, the answer you will get as 0, or else 1 with anything, same number, right? So this was the thing that was going on inside the multiplier, right? So therefore AND gate can generate all partial products, right? Like using the AND gate only, the multipliers will generate the partial products. Okay, after partial generation of partial products, we are going to add them using alpha adder or full adder. Okay, but in coming to the stage 2, like means partial product addition. Okay, after generating partial products, we add them together using alpha adders and full adders, right? So the reason it is called as array multiplier is because all gates are arranged in regular rectangular array structure. Okay, so this is what this is why the array multiplier is called a simple architecture, and this is the main reason why it's called as array multiplier. Okay, so why it's called as array multiplier? Because if you are learning some programming language, you know how the arrays are done, right? Like inside a array there will be some memory locations. They will be stored like side by side, right? If you imagine like how the memory looks like, means exactly you will remember them as in a rectangular shape. Okay, so in array multipliers, like all the gates are arranged in rectangular array structure. Okay, that's why it's called as array multipliers. So how does the array multiplier architecture looks like? Look here, this is what your array multiplier architecture looks like. If you multiply this a 4 bits input with a b 4 bit input. Okay, here your a is multiplier, sorry, multiplicand, and b is multiplier. Okay, so based on this, you are multiplying your first bit of b input with every input of a, right? Like that you are going to multiply. After that, 1 plus mark, like this is what a symmetrical image of your multiplier, right? You used to write this everything inside here, like this side, and after that plus. Okay, just like think this as a symmetrical end of the multipliers, and for this like empty spaces add plus, right? So that's what you are using inside a multipliers. Okay, so if you are create like just how the way they are stored, they're in the form of rectangular, right? And it's a form of array, like this will be a first stage, like first partial products where they are stored in the form of array, right? With side by side, so that's why they called as array multipliers. Okay, after multiplying everything, you're going to add them using half adders and full adders, right? So usually if you have 4 input and 4 input, obviously your output will be, what is the output you are going to get? 4 plus 4 8, right? So obviously you are going to get 8 bit output. Okay, so based on that only you are going to get the output. Okay, so this is what like how your array multipliers works. Like in previous class I explained multipliers, right? In the same form the array multipliers also is going to work. Like if you are going to multiply this first bit with this every multiplicand, then its amount looks like this, right? This is called as partial generation for first order. This is second, this is third, this is fourth. Okay, this is how you multiply 4 into 4 bit, right? So after multiplying 4 bit 4 bit, uh, this like this is you need to arrange them, right? But in while you are calculating them on on paper manually, you are going to like leave some space, right, for like writing plus, and then you will calculate the total sum of that partial products. But for just like a better reference for you guys to like to make you guys understand better, first bits, right? First bit is 1011, right? So I have written like this only. Whereas for the second partial products, I have shifted, like added 10 here. Why? Because if nothing is there means obviously there will be zero. Okay, so empty zero is nothing but empty value or off state. Okay, so for the third partial products there will be 2 plus, right? So that's why we added 2 zeros. For fourth stage 3 plus 3 zeros. Okay, if you add this, like for addition it will somewhat looks like this, right? So if you add all of this, okay, 10 1 1 0, this is what it looks like, right? So if you add this, you will get this value. Okay, so and after after knowing the better understanding of how calculation is done and how it's like arranged, you need to know the hardware implementation, like how much AND gates should I use for like 4 into 4 bit or n into n array multiplier plus full adders. So for that we have some formulas here, right? Okay, so just remember this formula so you can understand like how many hardware that particular array multiplier is required. Okay, so how many AND gates you are going to use? It depends upon n square. Okay, so for 4 into 4, what is your AND gates will become N square is nothing but 4, right? 4 fours are 16. Okay. Full adders. So for all adders, your formula is n minus 1. N is nothing but number of bits. Okay. So you have 4 into 4 row multiplier means how many bits? 4 bits. Okay. 4 minus 1, 3. So you're going to use 3 half adders. Full adders formula is this. If you solve this, you will get 9. And total gates is the formula is this. Okay. What is the formula? 3n square. Okay. What is the n you have here? 4. For 4 is 16. 16 3 is 48. So approximately inside 4 into 4 and array multiplier, there will be around 48 gates. Okay. Yeah. So this is how you are going to find out how many hardware components that are being used inside a array multiplier. So these are some advantages and disadvantages of array multipliers. So what are the advantages? Regular symmetric layout, easy to route in ASIC flows, simple designs, no complex encoding logic needed, all partial products generated in parallel, means fast generation, low design verification complexity, easy to pipeline. Okay, these are the some advantages. Okay, so just think how these advantages points have come. Okay, means now we just learned, right? They are rectangular shape, so that's why they call as regular and symmetric layout. And simple design means like it uses in the form of array, right? And there will be no complex encoding logic needed. So it is why it's called a simple design. All partial products generated in parallel means nothing but one like bit one of multiplier is multiplied with multiplier, then you will like that only second bit, third bit, fourth bit will be multiplied that multiplier, right? So this is how it's going to happen. So this all occurs in a parallel way. So that's why partial products are generated fastly and low design. Why? Because just like I said, right? They are in rectangular regular array. And after this, easy to apply means because it inserts flip flops between the rows. So that's why like it's easy to connect, integrate between each other, right? So disadvantages are so delay grows linearly with bit width. Is nothing means if your input is like 8 bit, 16 bit, 32 bit, or 64 bit, then the delay will occur. Why? Because obviously you are using full adders. Then if you are using that full adders for addition, then as the bit input bit is going on increasing means you will get the uh, propagation delay, right? So that's why delay grows linearly with your bit width. Large area for wide multipliers, like I said, it also do addition inside that. So if you have operating for like 32 bit, 16 bit or 64 bit, then obviously it will require to, the number of gates inside them will increases. So that's why the area consumption also increases. Ripple can chain limits operating frequency means that's I said, right? Propagation delay is because you are going to use full ladder like ripple carry full ladder and no optimal for sign multiplication. Okay, so these are the some disadvantages that are present inside the array multipliers. Like these are just some delay versus build comparison. Okay, so just like I said, right? For 4, the delay is less as the your bit number of bits is going on increasing. Your delay is also increasing in the rate is for array multiplier. Okay, so in both multiplier also there will be delay compared to your array multiplier. You can minimize your what delay. Okay, so and also for voltage tree, it was it also have some delay, but that it will be in the form of negligible. Okay, So just like you can't, we can observe these three lines, right? So considering the other two multipliers, delay like voltage 3 multiplier as some constant changes, right? Like the changes is some minimal, okay? So yeah. So next going to booth multiplier. So just think, okay, just think you have this example, okay? So this is your input bit. So what is the input bit? 0 1 1 1 1 1, right?